The Best of Our Knowledge explores topics on learning, education, and research. Coming up, the sun is the center of our solar system and our source of almost all energy. The space probe Solar Orbiter has been able to identify the sun's dual engines for fast electrons, which are explosive flares and coronal mass ejections. Being able to collect this data, researchers have uncovered the key mysteries about these sun particles. You're listening to The Best of Our Knowledge. I'm Madeline Reynolds. The sun is the center of our world, meaning our solar system, and where most all energy comes from. Even though we have uncovered a lot about this great big star, there are still more mysteries to solve. The space probe Solar Orbiter has been able to identify the sun's dual engines for superfast electrons, those being coronal mass ejections and explosive flares. These events are both types of space weather. Solar Orbiter has been able to catch over 300 space weather events close to the sun to be able to be used for research. This mission has been able to identify and solve mysteries as to how these particles travel and even sometimes appear late to an event. What this all can hopefully give us is a better understanding of how to improve space weather forecasts, protect astronauts, and help shield spacecraft. I spoke with Alexander Vamut, the deputy head of the solar physics section at the Leibniz Institute for Astrophysics Potsdam, to learn more.
The sun is our star, so to say. The sun is the star in our backyard. The sun is a quite normal star, but what makes it special, of course, is that it's very close to us. So on the one hand, the sun is, of course, extremely important for us. It gives us light and heat. It powers basically the whole climate and is a prerequisite for life on Earth. On the other hand, the sun is interesting because it's the only star we can really study from up close. So if we want to understand the cosmos, we need to understand galaxies, which are consisting of stars, so we need to understand stars. And if we want to understand stars, the sun is the perfect place to start. And the third aspect I would say that's really important for us is that the sun is really an active star, so it changes in time. Also on quite short time scales. This is what is called solar activity, or when we speak about the influences it has on us, we speak about space weather. So the sun is magnetically active. Solar magnetism drives eruptions, and these eruptions can hit Earth and interfere with technological systems, for example. So therefore, there's also a very practical relevance of this area of research.
So in the research article, it states that the sun is the most energetic particle accelerator. So I'm wondering if you could just explain what that means exactly and how it affects Earth and the space around it.
Particle accelerators on Earth, which accelerate charged particles, ions or electrons, to speeds close to the speed of light. This also happens on the sun and in interplanetary space. So these solar eruptions can really accelerate charged particles up to these high velocities. Therefore, these particles are very energetic. There are other configurations in the solar system where particle acceleration happens, for instance, in the magnetosphere of the planets. But the sun is much more energetic than that because, of course, it's much larger and also the magnetic fields are significantly stronger. What are the influences? Those particles, especially the ions, so the heavy particles, they are so energetic that they will just go through your spacecraft and deliver a significant radiation dose. So this can damage the delicate electronics on satellites, for example. But it's, of course, also not very healthy for astronauts because we can equate these particle showers with a really high radiation dose. So these are the space weather aspects of these charged particles.
So I'm wondering, how did you conduct your study into the sun and the particles?
Yeah, so we are participating in a mission that is called Solar Orbiter. So that's a spacecraft that is orbiting the sun, which was launched in 2020. It's a mission mostly conducted by the European Space Agency, ESA, with a contribution from NASA as well. And the aim of this satellite was basically to do two things: to understand this magnetic activity of the sun, and to better understand how what happens on the sun links to what happens farther out in interplanetary space. So that the mission was specifically designed to do these things. And for instance, when it comes to our study, we are interested in where are the particles accelerated at the sun and how do they propagate outwards to Earth. And therefore we have two kinds of instruments on board. One are the so-called remote sensing instruments, which are basically telescopes, which look on the sun and record what happens there. And the other set of instruments are the so-called in situ instruments, which basically observe the local surroundings of the satellite. For instance, the energetic particles that hit the satellite are measured by this type of instrument. And our aim is basically to link together what happens on the sun and what finally arrives in interplanetary space or at Earth.
So what are solar energetic electrons? There are two kinds from what I've read in the research. So can you identify both of them and explain exactly what they are?
Yeah, so actually that has already been known since quite some time, that these electron events, so basically these are beams of electrons that are launched from the sun into interplanetary space, they come in two different categories. One of them are the so-called gradual events, which also have a quite gradual time profile, so they have quite long duration and show a rather slow rise. And it's important to understand that these electron events, they are also most of the time also associated with ions. So it's not just the electrons that are coming from the sun, but also ions like protons and heavier elements. And the composition of these ions, meaning the abundance or the number of different elements in those gradual events, is the same as in the quiet sun. In the impulsive events, on the other hand, these are much more shorter-lived and they rise very quickly. They are also more narrowly beamed. In these events, we observe then ions that are highly enriched in certain types of specific ions. For instance, there is helium, so that's the second most common element on the sun after hydrogen. And helium comes in different isotopes. Helium-4 is the normal one, but there's also a small percentage of helium-3. And this helium-3 is highly enriched by orders of magnitude in these impulsive events. So we can use basically the ion composition to group these events into two categories. And for a long time, it has been suspected that these two different types of events are also caused by different phenomena at or near the sun.
You're listening to the best of our knowledge. I'm Madeline Reynolds. If you're just joining us, we're learning all about sun particles. Thus far, we have learned some basic functions and characteristics of the sun. We also learned that the sun can charge particles to travel at the speed of light, as well as the two types of solar energetic electrons that exist, which are impulsive events and gradual events. We will continue to learn more about the sun with Alexander Vamut, the deputy head of the solar physics section at the Leibniz Institute for Astrophysics, Potsdam. So we know that solar energetic electrons are actually products and the result of solar flares and larger eruptions of hot gas. Can you explain both of these phenomenons and what happens when they occur?
Mm-hmm. So both of these phenomena are results of the magnetic activity on the sun. A solar flare is a more localized phenomenon which happens in the corona of the sun, so the hot outer atmosphere. Basically, what always happens in these solar events is that you convert energy that is stored in the very complex and strong magnetic fields of the sun, and you convert a part of this energy into other forms of energies. For instance, you heat gas, or you accelerate particles to very high speeds. So this is what happens in solar flares. We know that electrons and also ions are accelerated there. A large fraction of those particles rains down into the deeper layers of the solar atmosphere. There they interact, they lose their energy, they heat plasma, and we can observe the resulting radiation. This is what our remote sensing instruments, our telescopes, see. And another fraction of these accelerated particles has access into interplanetary space and flies away from the sun. And if we're lucky, they hit our satellite and we can measure them. So these are the solar flares. Coronal mass ejections are a more large-scale phenomenon. Still, it's the magnetic fields that play the major role here. Also, flares and coronal mass ejections are actually tied together. I would say they are two consequences of the same underlying phenomenon. So coronal mass ejection, we look more into the plasma that is ejected from the sun. So in coronal mass ejections, large clouds of gas, of plasma, and embedded magnetic fields are launched away from the sun, and they propagate into interplanetary space. And along these, they are quite fast, so they can drive shock waves ahead of them. And these shock waves are very efficient in accelerating particles. And we know that this happens at these shock waves. So we have two potential sources of energetic electrons, or energetic particles in general, the flares and the CMEs. And the question is, which one is responsible for which phenomenon, or do they act together? And basically, what causes what?
In the research article, it points out that you and your team detected the solar energetic events at different distances. And when you did, you saw a lag. So I'm wondering what exactly that lag is, and if you could explain to us what exactly that is.
Yeah, that's a long-standing question in this research area. So we know when an event happened on the sun. With our telescopes, we can observe both flares and coronal mass ejections, and we can detect the particles that arrive at the satellite. We can then reconstruct the time at which the electrons, in that case, at which the electrons left the sun. And all the studies that have been conducted over the recent years and actually decades, they found that in most cases the electrons appear to be launched from the sun only after the flare or the CME happened. We would expect that they should be synchronized, but there are distinct time lags of typically 10 minutes or even more. In some extreme cases, it can be over an hour. And the question was, are the electrons really launched later than the actual flare or the CME, and why is that? Or is this just an apparent effect? Maybe something happens to the particles while they travel from the sun to the Earth or to the spacecraft, and basically delays those particles. And the delay is not really real. They're actually launched at the time of the flare or the CME, but we just detect them later due to some transport effect.
So I think it's important to note that the space between the sun and the planets, is not empty. And I think that's a point that's also made in the research article. So could you just explain and identify what is there in relation to the research?
Yeah, exactly. I mean, normally we consider a space to be quite empty. It's a vacuum. That's not really true. So the solar system is filled by a very tenuous gas. So it's close to a vacuum, but it's not really a vacuum. The whole solar system is filled with this hot gas, which comes from the sun. Basically, the corona of the sun, the hot outer atmosphere, expands into space and fills our whole solar system. This is called the solar wind. So that's a constant stream of hot gas that comes from the sun, which typically has speeds of between 400 and 800 kilometers per second. And this gas also carries with it magnetic fields from the sun. So basically, the space between the sun and the Earth or the spacecraft is filled with a hot gas and with magnetic field lines. And of course, particles, especially charged particles, then cannot just propagate straight from the sun towards the observer. Since they are charged particles, they are tied to magnetic fields, so they have to follow the magnetic fields. And depending on the path the magnetic fields make, the particles have to follow. And it's easy to imagine that if the magnetic fields are quite complex or if there's some turbulence, these particles could have traveled longer than we actually assumed. And so therefore you could have these delays. And what we now can do for the first time is to probe this, because up until now, most of these observations have been done from near Earth, so from a fixed distance of 1 astronomical unit, the distance between sun and Earth. But now with solar orbiter, since we fly close to the sun, to about a quarter of the distance between sun and Earth, we can observe these events at different distances from the sun. And so if there's really a propagation effect, if the electrons are really launched at the time when we suppose they should be launched, at the time of the flare, at the time of the CME, then we should see that there's this delay we observe is increasing with distance from the sun, right? Because there is some effect which apparently slows down the particles, and this should add up the farther we are from the sun. And with solar orbiter, we could really show that this is indeed the case. So when we observe events close to the sun, we find rather short delays. And when we're at about the distance of Earth, we see the typical delays around 10 minutes. So we could show, yes, indeed, at least partially we can understand this delayed arrivals due to propagation effects which are tied to the interplanetary magnetic field and its turbulence.
You're listening to the best of our knowledge. I'm Madeline Reynolds. I've been speaking with Alexander Vamut, the deputy head of the solar physics section at the Leibniz Institute for Astrophysics Potsdam, to learn more about the sun. To catch you up to speed, we have learned that these events we have been talking about are actually space weather events, which are explosive solar flares and coronal mass ejections. This then results in electron particles. We also learned that a lag happens with particles that arrive to the site after a space weather event, as well as how space is actually not empty like we think. There is hot gas that fills everything up that emits from the sun called solar wind. I continue to uncover and learn more about the sun with Alexander. So in the research and when I've been talking to you, you've kind of categorized these events as being, quote, space weather. So with the findings, does this help us at all have, one, a better understanding of space weather in general, but two, does it help us have a better understanding of how to keep satellites, spacecraft, even people going on missions in space safer, but also us here? Does it help us understand how to maybe battle these events, for lack of a better term, in terms of solar flares, of how they could, disrupt our technology in some ways? Is this going to help us, these findings, at all?
Yeah, so the events we observe form a part of space weather. It's not the only part. For instance, the CMEs I talked about, they can directly hit Earth, or better said, the magnetic field of Earth can interact with that and cause geomagnetic storms. So this is a different type of effect. But generally, we need to understand better the acceleration of particles at the sun and their propagation in space. For space weather, the ions, so the heavier particles, are more relevant because they represent a larger radiation dose. However, looking at the electrons has one advantage. We have better remote sensing data of them. So with our telescopes, we understand better what the electrons do close to the sun. So for instance, we can observe them in X-rays, and we can observe them also in radio waves. And especially those radio observations help us to tie together what happens on the sun with what happens in interplanetary space. So we know quite a lot about the electrons, which is difficult to observe of the protons. But of course, better understanding electron acceleration and propagation will also help us to better understand what happens to the ions, which are more relevant to space weather. So yes, there is a connection, but with our research, we have not yet solved the issues of space weather. But it is one element.
So, for you, what was the most fascinating aspect of the research?
Basically, it was the experience of working together with such a large team, because on Solar Orbiter we have 10 instruments, and 8 of those instruments participated in the study. So I had the pleasure of coordinating this effort and working together with the different instrument teams, and that has been a great experience because it's a unique experience to work together with so many people who are really enthusiastic about what they do, and it's really been a pleasure. And of course that research has not ended yet. We will continue to observe as the mission progresses. So that's on the personal side, I would say. And on the scientific side, it was really this finding that we could find the first indications for these propagation effects, so that indeed the particles are not launched after the time we see the events, but something's happening between the sun and our spacecraft that gives these apparent discrepancies. And of course, that will be in the next few years really a key of our research, to understand what is actually, which mechanism is behind these transport effects.
So my final question to you is actually, what are you excited to research into next regarding this topic?
Yeah. So I already answered parts of the question. So we need to understand basically what's behind these transport effects. Then the second aspect we will now look more closer into is looking not just at the times when the particles arrive, but looking in detail at their spectra. So typically these energetic electrons show spectra that are called power laws, but I mean, that's not really important. Basically, we have a lot of electrons at lower energies and a rather small number of electrons at high energies. And this is characterized by this power law. We can observe that for the electrons we measure directly at the satellite, but we can also use X-ray observations to infer how the spectrum of the electrons looks like at the sun. This has also been done in the past, and what we found is, yes, the spectra of those electrons at the Sun and in interplanetary space, they clearly correlate, so there is a relation, but it's not like we suppose the relation to be when we apply the typical models we have. So still there's something which is not understood, and we will probe now whether this discrepancy is again due to some transport effect. So maybe we find a better agreement between the spectra when we are close to the Sun, or whether that's really a real effect. Maybe the electrons which rain down on the Sun are different than the ones which go up into interplanetary space. Maybe they are accelerated by a different process. This we can now probe in detail with a large number of events for the first time, since we do this at different distances from the Sun. And finally, what we really want also to exploit is multi-spacecraft observations. So Solar Orbiter is, of course, not the only spacecraft which observes the Sun and which also observes particles in situ. There's a whole fleet of spacecraft at the moment which is capable of doing these measurements, or at least 5 or so, all over the inner solar system. And with that, we can, of course, constrain the extent of these particle beams. So are the particles really injected only into a very narrow cone, or on a very broad front? And we know that especially those gradual events, they are often observed nearly 360 degrees around the Sun. So they are launched really on a very broad front. And the question is, how can that be? Are they really accelerated at a very broad front, like a very large CME? Or can the particles basically drift along, or not along the magnetic field, but transverse to the magnetic field to get to these large distances? And we have the capability now to do that, since we have all those great spacecraft which are active. And now it's just a question of working together with the other spacecraft.
That was Alexander Vamut, the deputy head of the solar physics section at the Leibniz Institute for Astrophysics, Potsdam. His research was originally published in the journal Astronomy and Astrophysics. If you'd like to tell the best of our knowledge what you think, send us an email at knowledge@wamc.org. You can listen to the best of our knowledge anytime as a podcast, downloadable wherever you get your podcasts. If you want to catch up on past episodes or hear more WAMC National Productions programs on the news, academic study, books, women's issues, the media, and the environment, visit wamcpodcasts.org. This has been The Best of Our Knowledge, episode 1829. The Best of Our Knowledge is a national production of WAMC Northeast Public Radio. The latest on all National Productions programs is available via the Airwaves newsletter and our flagship station's website, wamc.org. Until next time, I'm Madeline Reynolds.